We're going to look at numbers 10, 11, and 22 from chapter 9. In this example, you are looking at the ability to predict the weather patterns of hurricanes. And you can see the chart in the top. Here we can see that we have a pretty wide range of error, wide variety here, a lot of variability in the answers. But as time has progressed, we can see that that ability to predict has gotten better over time. In other words, the error has gone down, but also the accuracy of those predictions, in other words, the variability here is shrinking, and so they're getting a lot more consistent results. So at some point, I guess 25 to 30 years after 1970, we had a pretty solid ability to predict, right? That's just what we're looking at. So part A says describe the slope and intercept of the model. Here again, I wrote down the slope is negative 5.23. For each year since 1970, we'd expect the error to go down by about 5.23 miles on average. Keep in mind, when I write out these kinds of values, I want to make sure that I'm using the right value here. I've got the sign. In this case, I'm using down to indicate it's a negative value. And I'm using the variables years and error to describe it. If I were to do y-intercept, that value is 292.089, right? In the year 1970, because that's at year 0, we would expect the error to be about 292.089 miles as an estimate. Letter B, explain the SE. This is the standard error of the residuals, right? How off my predictions are going to be on average. And that's kind of how I said it. We would expect our predictions, our y-hat values, right, to be off, or we would expect it to be different from the actual values by about 42.87 miles on average. Part C asks me, do you think that they would be able to hit 125 miles by 2009? Yes or no, and why? Well, we can check. We have an estimated value. We have an equation up here. We can try to predict for that time frame. So I'm going to plug in 39. If you look up here, they're using values since 1970, so 2009 would be year 39 in that counting method. That's important. We note that because if I were to plug in 2009, that would be 2009 years after 1970. So we would definitely get an incorrect value. So plug this in, I get 88.5. So yes, assuming the trend continues, right? We don't know. This is a little bit of extrapolation. It's not too terribly far away from that, and we would have no reason to think that the trend would change, but I'm going to tell you why I think it's so. I can plug it into the formula. My value drops well below 125. I think we can actually see that we achieved that value before 2005. So I think that is a definite, almost a guaranteed value, right? We're not going to get worse if you look at it this way. But I can see here that my model even predicts it to be that way. Part D says, would you think they're going to get 90 miles? And I'd say yes. We plugged it in. We got a value that was below 90. And so because that has happened that way, I would predict it, here again, assuming the trend continues. And they kind of say, what kind of issues do you think? Well, this is extrapolating. I don't really know if the trend is going to continue like this. It may continue like this. And so we would say, assuming that the trends continue, we would be able to say that, right? But here again, we're extrapolating. This is not something you typically trust when you do something like this. This is number 11. I'm going to do two of these. I'm going to do A and B. You can look this answers up in the back of your text. So I'm just going to kind of go over the first two. The rest of them kind of follow the same pattern. In graph A, the question is, why would we consider this point unusual? Well, this point is definitely an outlier or a potential outlier in the x direction as well as the y direction, right? So we would expect values to fall somewhere in between this y value and then in between these x values. This one tends to fall way beyond the x and y values, which makes it considered a possible outlier. Would you call it high leverage? Yes. Right? If the farther down the x-axis this value gets, it has higher leverage, right? At least, especially compared to any other dots in the list. Would it have a large residual? Answer is absolutely not. My line of best fit is going to kind of run right through the middle of that, and it's going to go right past my dot, if not touching my dot, right? And so that line of best fit, how far would my dot be? It's going to be almost on the line, if not already on the line. So the residual here is going to be very minimal. Number two, Do you think it's influential? If I cover up the point, right, if I cover up that point, I don't think the line of best fit is going to change at all. I think this is going to be right in line with everything else. So this point is not at all influential. 3, if the point were removed, would the correlation be stronger or weaker? If I take a point off of my line, I'm going to make that R value weaken. Probably not by a tremendous amount, but I've removed a point from the line. So there's less points on my line, so my R value would get weaker. And 4, if you remove the point, what would happen to the slope? I do not think anything would happen to the slope here. I think this is right on the line, so by removing that point, I think my line of best fit is going to stay about the same. Now, we can contrast that with graph B. Here, if you were to kind of just cover up this point, you would think the line of best fits would have a slight positive slope to it, right? Either 0 or a slight positive trend. And if I look at it, do I think that this this point is influential? Absolutely influential. How is it different? This is an outlier in the x direction. It's probably considered an outlier in the y direction. It's just not as extreme as the x. And so this point is definitely well away from the group. I would expect it to be a much closer to this set of data before I would think it would be not considered an outlier. Is it influential? Yes. If I left that point out, I think my line of best fit is going to kind of maybe do it in this kind of idea. If I keep the point in, I think my line of best fit is going to go down like this. I think it's going to drag it down so far that it's going to be pretty close to that point. It might not be right on it. It'll be just above it. But it's going to try to come down, and it's going to try to keep that point. So it's going to be somewhere in this range. So yes, I think it's influential. If you remove the point, will the correlation be weaker or stronger? This one's kind of difficult to determine. A lot of it depends on how close my line comes to this point. If that line just barely drops a bit, I think it would weaken R. If that is definitely influential, we don't really have any values here, so I don't know exactly how far away it is. If it's coming down right to it and I remove it, it's going to make R weaker. So in that case, I could see an argument in both directions. It kind of depends. We really needed to have numbers there. So I would say it might change it in a moderate sense. If the point were removed, would the slope increase or decrease? Well, if it's there, the slope is definitely going to be in a negative sense. And when I remove it, it's going to at least go up. It's going to go to 0, or it's going to go to a very small positive value. So the slope will increase once I remove this point. Okay. In graphs C and D, you can kind of take the same approach. You can look those answers up in the back of your book. For graph 22, well, for problem number 22, we're gonna kind of introduce this idea of what it's talking about. Here you have the different age groups between men and women when they first get married, right? Back in the late 1800s, it was about 26 for men and 22 for women, and that age difference was about 4 years, right? And then it kind of trends along the lines, and you have that age group kind of narrowing as times got more and more modern. All right, part A. What's the correlation? Well, I've got the R squared value right there. I can take the square root of it, and I get positive 0.87. However, I have to look at my trend. The trend in this problem is negative, or I can see that negative value in the slope. Remember, R's value always matches with slope's value. If it doesn't, you're wrong. That R value is wrong, and it's going to happen when it's negative. Obviously, if we don't think about it and slope is positive, I'm really going to kind of get lucky, and I'm going to end up with a positive 0.7 anyway. But when it's negative, you're going to be careful. You're going to miss that part of it. B, interpret the value of slope. My slope is this really small decimal value here. It's always the second number in this coefficient list. We would say for each additional year, or for as the years progressed, something like that, we would expect the difference in the age, right, that's the y value, to go down by 0.0166. I just kind of estimated that number, years on average. Okay, part C, it's asking us to say, predict the age difference in 2015. This is important, right? In the previous question, we had to abbreviate the years because it was from 1970. Let's look at this value. In this example, it looks like they're using the entire year for the variable. So I can go ahead and I can plug that value right into my equation. I can look up here and I can get the y-intercept from that value. the slope from this value, and I can plug those in to create my line of best fit. And for x, or for in this case, the year, that's the x value, I'm going to plug in 2015. And if I plug it in now, if I keep this entire decimal place, we're going to get 1.68. If you abbreviated this, I think in class today we use 0.017. This actually drops quite a bit, almost in half. It drops to 0.87 or something, 805, I think it's 0.805. So depending on what you're using here, I decided to go ahead and use the entire decimal point because it's not that big a deal. And so we think the age difference dropped to about 1.68. And the question at the end asks, describe the reasons why you might not place much faith in that prediction. Number one, 2015 is quite a bit of ways away from the last bit of data we have. It's 15 years past. Now, this trend cannot keep going forever. Eventually, you would get ridiculous answers. You would get some kind of weird answers that the difference would be so great that it wouldn't even make sense, right? So we know that that trend cannot progress forever, but this is extrapolation, so just by the nature of what it is, I don't really trust it. We would expect that trend to continue, but it is not guaranteed, right? I think would the age drop to 1.68? Here you're already down at 1.6, right? So the line of best fit's kind of in this pattern. It doesn't fall down to that exact value, and so it's kind of above that line here. So this is my prediction. Do I think that's accurate? It could be. It doesn't seem unreasonable at this point, but beyond that, we would know that eventually it would get somewhat unreasonable. So that's kind of why I wouldn't trust that kind of result. Hope these helped. If you have any other questions, please let me know, and we will talk about them in class later on.